started. Finish up chapter 4. Go on to chapter 5. Okay, so this is how you actually remove an outlier. As we mentioned before, if you just tried to do this visually, you are going to probably screw up badly. And there is very high profile, people believed it for 40 years. Government grants were given in the billions of dollars to support research on it. Cases of eliminating data that causes complete misunderstandings of what you're seeing. Remember last time I talked about the lipid theory? Okay. I'm not joking. That was billions and billions of dollars wasted on a theory that had no actual support because that guy eliminated 34 of the 36 data points with no statistical reason to do it at all. Just, I don't like these data. And if he would have bothered looking at any of the other 34, he would have very quickly realized that there is no correlation pattern at all. And it's very obvious if you've ever been to Northern Europe. Seriously, look into Northern Europe. It becomes incredibly obvious that lipid consumption, having a high percentage of your diet be lipids, has no correlation with heart disease at all. In fact, the reason cholesterol increases for heart disease and builds up in your arteries is because you have a heart problem in the first place. And damage is being caused, and what do you need to repair damaged cells? Yeah, lipids, right? Specifically cholesterol. So, yeah. It's just terrible science that's caused damage and destruction throughout the world and probably thousands of deaths. Anyways, this is the lesson somebody should have taught that SOB. World would have been a better place. So this is the Grubbs test, okay? It's going to help you decide whether a questionable datum, an outlier, should be discarded. So you're going to take a value and you're going to say, I don't think that value is right. I think something happened. Like, I think the person spilled and that's why they got low value, okay? And they didn't do a good job recording it. Or, you think maybe you screwed up, but you're not sure. So you go ahead and do a Grubbs test on it, okay? And so right here, we see the mass loss of 12 galvanized nails measured. This is the percent mass loss right here. So those are our data points. Here we have our mean and standard deviation. So should we accept or discard this 7.8 value, which is our lowest value? And notice, by the way, one of the ways you can help yourself figure this out is if something's quite a bit larger than your standard deviation from your mean. See that? Like, this is a little bit larger than your standard deviation from your mean, but this one's like twice your standard deviation, right? So we go G calculated. We take the questionable value minus your mean, divide it by the standard deviation. So we get a G calculated of 2.13. We would then go to the G table, which is table 4.6, I believe. That's the number the example thing gave me. It's actually from your book stuff that I pull, but they always give me weird stuff sometimes. So in this case, we see that G calculated is less than G table. We should actually maintain this questionable data point. We cannot eliminate it. This is within the realm of random error.
So,
it's on the tail end, but...
When you're looking at G table, is it based on the amount of data points you have?
Yeah, it's going to be based on the number of data points you have. All these are based on the number of data points because they're all actually methods of determining, is this within random error? And the larger, your random error is going to be larger for a smaller subset of data, right? You can shrink it in a square root fashion, by adding more sets of data, right? Yeah. For example, if you just did one measurement, your errors can be huge, right? And you really don't know, because keep in mind when you're looking at random error, they're Gaussian relationships. Remember, a Gaussian curve actually comes out and does a huge tail, right? So there's like a 1 in 100 chance that you get values that are just 10 standard deviations off, just by random error, okay? So those do exist. All right, so the method of least squares, you guys probably know this, I hope. You've probably taken Excel and you fit a line to a scatter plot, right? Okay, and if you looked carefully, that line was called a least squares line, right? So the method of least squares is used to determine the equation of your best straight line through experimental data points. Best being, of course, a set of assumptions, right? This has a linear line, of course, that is y sub I equals m times x sub I plus b. These will be data points you'll provide, typically through an experimental method, whereas m and b will be your slope and y-intercept, right? Please note that because you are, I'll talk about down here actually. So this is going to use the equations 416, 418, 420, 422 that would provide your least square slope and intercept and their standard uncertainties. I'll be very honest with you, this is not worth you ever doing by hand. Like, the only reason you'd ever do it by hand is because you have to. You absolutely have to, because something went terribly wrong, okay? Do it using Excel. Because if you do it by hand, you really can't do anything over like 10 data points. It becomes hours of work. It's just too long. So, yeah. But computer can do, thousands of data points in a second. And do you guys know that Excel has an equals slope, and then you can take the data set you want the slope for? So you can make a chart, but you can also just use Excel to get the numbers. So you can go equals slope, parentheses, put the data set you want in, and it'll give you the slope. You can do the same thing with the y-intercept. You can do the same thing with the errors, so you can just get the values. You don't have to read them and record them each time, okay? So make sure you try that sometime. There's examples in your book that you'll end up doing. Make sure you do it, okay? It really is far more useful than graph, and now I have that equation on my graph, because automatically you can port those numbers into other equations, right? You don't have to write them out every time. And sometimes the graph doesn't give you enough decimal places, right? If you have something that's very accurate, has very low uncertainty, it could give you not enough decimal places. Because, the computer scientists didn't know. So the independent variable goes on the x-axis and the dependent variable goes on the y-axis. What does an independent variable mean? Let me ask this from a different direction. So notice that our best straight line is being fit to what? The y-intercept, not the x-intercept, right? So we're fitting things and getting errors for our y values, aren't we? So where should our errors be? My y values. Those should be the results of my measurements, right? And then my x values are going to be typically the things that I have control over, right? And yeah, you were right. I just wanted you to think about it from both directions, okay? So my x values are the things I control. My y values are the things that are results of that. Or I think are results of that. They could not be. In which case you get a non-correlation, right? Which is fine, by the way. That's good science. And you can publish non-correlations. You know that, right? I have published non-correlations before. Some of the best results in science, the biggest names, are non-correlations, that they disproved that these things are correlated. Okay? Those are just as important as finding correlations. In fact, that's how science works, right? You eliminate all the stuff that's not correlated. You're left with the stuff that you go, right now. Keep trying. Okay, so find the best fit line through this data. We just have a small number of data points, because honestly, if you try to do anything bigger, it would be impossible. It's just too much work. By the way, what happens if I only have 2 data points? So let's say I collected 3 data points in a study, and I use a Grubbs test, and I eliminate one of those data points. Well, any 2 points in space make a line, right? Literally any 2 points. So if I have less than 3 points, I can't do this. There is no statistical anything about it. It is literally 2 points in space make a line. That is facts. I have actually seen a PhD in biology present a paper. That's what the person said. He said that. He goes, I have these 3 points, and it was, 2 points and then 1. And he had his line, didn't really look like a good correlation. Shitty correlation. Because the data wasn't correlated. And he goes, well, this point's really far off, so if I go ahead and just take these 2 points, I get a really great fit. Well, fucking duh. Literally, you always get a good fit with 2 points, right? There is no error. Jesus. And how he thought he could eliminate 1 point, right?
I'm also trying to figure out, would it be possible that that one that was the outlier that he got rid of is actually correct and the other 2 could be wrong?
There's no way to know ever. Like, with 3 data points, you don't have an outlier. Because every single one would have equal weight, right? It would, there simply is, because you'd have 100% fit if he got rid of any 1 point. Would give you 100% fit for the line through the rest. So it was a ridiculous case, right? It's sad that was an actual person that thinks they're a scientist and has some sort of certification saying it. I don't even, shit. That was when I was an undergraduate. I went to a ACS meeting, and that person presented at a regional ACS meeting, which is the next step up from what you guys usually went to if you go to the ACS meetings around here. So anyways, this would be your equation. What am I looking at? Y equals slope times my x plus y-intercept. Yeah, there's my y-intercept. I'll be very careful about setting y-intercept to 0 like the program typically wants you to do. Okay? Unless you know that it absolutely can be set to 0, don't do it. You don't. You let it find it. Yeah. Remember, that's actually what you're doing with this. A least square finds the slope and the y-intercept. Those are the 2 data points it finds. An interesting side note is to find 2 data points, it actually needs at least 3 data points. Do you know that? And to find 3 data points, you need a minimum of 4 data points. You always need at least 1 more data point minimum. Anyways, right here, this r squared, what do you think that is? How well fit it is, right? Yeah, it's correlation factor. Yeah, the higher the better, right? It should be 1 if it's well correlated. Okay. Anything above 0.9 is pretty good, well correlated. Okay. By the way, this y-intercept actually tells you something. Okay? Like if you do a spectroscopic study, if you have a y-intercept that's not 0, that's like 1 at an x of 0, that typically means that your concentration being 0, you're still detecting signal. Meaning you probably have something in your blank that you haven't accounted for. So that actually tells you data, okay? The y-intercept is data, it's telling you something. Don't think it's not. So in order to make a best fit line, we're going to minimize the magnitude of the deviations of yi minus yi hat from the line, i.e. you'll minimize the deviation from the line to your data points in the y coordinate, okay? Which is why I keep stressing that your error is all calculated, your fit is all calculated from your y coordinates, right? So you need to be very careful. You really do need to put your independent variable on the x. It becomes much more difficult to figure out your error if you put your dependent variable on your x, okay? Because that's how the equations are set up. So we want to minimize the total residual error. Because we minimize the squares of the deviations, this method would be called least squares, the method of least squares. And notice that again, you're taking this total residual error, you're minimizing it. Your total residual error is the sum of your errors squared. So literally the squares of the residual error summed. These are the equations we talked about. Notice they are matricy equations. By the way, you can do all of calculus through matrix math. You don't have to do it using the calculus you've learned. And in fact, that's how computers do calculus. And honestly, I wish they would teach more matrix math. And I kind of wish they would just minimize calculus, because most people use computers to do most of the more difficult math anyways. I think it'd be more useful to go on to matrix math, but whatever. There's also non-Newtonian and Newtonian calculus, by the way. There's actually 3 types of calculus with different symbols. They're all invented about the same time. I used to know a professor who used the non-standard calculus. And it has like dots and stuff instead of D for derivatives. Really smart guy. There's some cool stuff you can do with the other calculuses that are easier using them. God, that guy was so smart. We can talk sometime about him. He's really interesting guy. Really cool. Operation of determinants. This is how you do the operation of a determinant using a matrixy. I'm not really going to go into this. I'm going to kind of just leave it here because first off, I don't think you guys have a whole lot of experience with matrix math, or matrixy math, I should say. And matrixy maths? Yeah, well, whatever. I guess I'm not English. I don't need to do maths. Anyways, it's, yeah, this is how you would do that, okay? And this is why it's so much easier with computers. Even a simple problem in this would take you hours because humans just aren't very good at it. Calculating the uncertainties, these would be the equations to calculate your uncertainty in your y-axis. So you remember how you can propagate uncertainties? This is the propagation of uncertainties for a least squared fit. Okay? So equations for estimating standard uncertainties in y and the slope and the intercept b are given here. Here we have the uncertainty in our y. Here we have the uncertainty in our slope. And here we have the uncertainty in our y-intercept. And so you plug these in. Yes, these are differences. D for differences, right? Does everybody know what the I stands for in these things?
Is that like the changing value?
Yeah, changing value. It's the each y point, right? So we have 6 y points. So you put one difference in, and the next one's difference. You get the point? Okay. And remember, these differences would be from our fit line. Okay? I think that pretty much does it. This would be an example of these calculations. Notice even the book stuff is probably an Excel spreadsheet, right? Looks like it. I'm sure it is. Because you don't want to do this shit by hand. It's just very unpleasant. Okay? Yeah, here we have the sums, by the way. These are differences. Differences squared.
What is the uppercase D in
I'm 95% sure that's degrees of freedom. But I would like you guys to check me, okay? Because I am kind of tired. And there is a possibility I'd screw up this morning. I did not get a lot of chance to prep, and I am 29 credit hours is too much. I'm exhausted. I've been having to do paperwork and set up classes for 3 weeks now. Everybody else is gone, and I'm still here doing that. All right. So this is calculating our uncertainty. So equation 427 estimates your standard uncertainty in the x from a measured value of y with a calibration curve. Notice the complexity of this equation is significantly greater, right? Do you see this? Yeah. And that's why you want the thing that you want your uncertainty from to typically be in the y. If you're going to calculate uncertainties, you're better with it being in the y. But yeah, if you need to do the x, this is the equation. It has all the different parts of it. Do you guys have any questions?
Is there a way of putting that in Excel?
Yeah. Oh, yeah. What I recommend is if you ever need to do an equation like this that has this number of components, what you do is set up your Excel so it has a K and it has a cell. An N, it has a cell. Okay? Set that up first. Take a piece of paper, plug those cell numbers in for these variables, and then solve the equation until you get what you want. The equal sign at the other side of the equal sign is the result of the cell, right? And so you solve it down as much as you can first.
So don't put like 71 or like 1A divided by.
Yeah, I would. That's what I would do. I'd have it like A1 divided by absolute, and I'd go ahead and start writing those out like I would. ABS, parentheses, and then that would be, whatever, B1, etc., okay? Yeah. But you can sometimes simplify things a bit. The biggest problem is going to be matching your parentheses, but Excel helps you with that by changing their colors. That's where you usually start screwing things up, is getting your order of operations out of order. So that's why I say you always want to do it on paper first and put all your parentheses in. Like you're going to need a parentheses around this, then a plus. So this would be this term here, a cell divided by absolute cell, times square root, parentheses, a parentheses 1 over a cell, in parentheses plus a parentheses 1 over another cell. Or if you want to be even more tricky about it, you could actually have it automatically count the number of cells, the number of data points by doing count A. That's what I normally do when I do this. I'm about 90% sure that's degrees of freedom. If you were sending me an email, I can double check. If you guys can't find it, let me know. Typically, little d, unless it has df, which is degrees of freedom, little di is differences in these equations. But if you send me an email, I'll look. Calibration curves, this is actually incredibly important, but just sort of gets thrown in here. A calibration curve is going to show the response of a chemical analysis to known quantities. This is like the calibration curve you did for Beer's law, if you remember back then. And you'll do it again later on this semester when we do the spectroscopic. You're going to make standard solutions. You know those concentrations. You would plot those concentrations as your x. This would be your absorbance. You typically want to do absorbance because it's a logarithmic scale. Otherwise, transmittance would give you logarithmic response. And you'd plot these. You can fit a linear line as long as it's in the linear range. However, you guys may have noticed when you're mixing up solutions, at first it's a linear response, right? Double concentration, double the amount of light it absorbs, right? But after a while, what happens? Yeah, it gets so dark it tails off, right? And the portion that you can still see the differences is called the dynamic range. So the dynamic range is everything where you can add more and still see the difference, okay? And still detect the difference, I should say. But we're talking about eyesight right now. Nope. Nope. The difference will be so small that you can't detect it any longer, okay? And so you don't know if you've increased the concentration after dynamic range. You won't be able to detect it. By the way, this changes depending on the instrument. This is not constant for all instruments all the time. The dynamic range can change and the linear range can change, depending on the method and instrument you're using.
So is the dynamic range found through like your own calculations on Excel, or is it found based on like the different instruments?
You can actually usually figure out dynamic range just by eyesight.
Yeah, like seeing if like numbers are changing very much.
Yeah. Literally, it's just if it changes. If it stops changing, you're outside dynamic range. A side note to this that I'm just going to bring up because real-world application-wise, this really matters. There are many instruments that if you go beyond the dynamic range, you could damage them. Okay? So like I used to use an ICP-MS, which is an inductively coupled plasma mass spectrometer. And that thing was like $50,000 per fan. It was like a $500,000 instrument. And every sample always had to be diluted significantly because it was very, very responsive. It could pick up even small differences in concentration. But its dynamic range was actually fairly small, and it could actually get damaged if you put too much. The signal would damage the internal components. Never when I used it, so. But I wouldn't be surprised. There were a few times it was down, but they didn't tell me why. So maybe somebody else could have been using it and did it. I was always very careful. I'm not paying $500,000. So when there's that did happen in a microwave experiment though, where we had our diffusion pump stopped working. Diffusion pump is a pump that's made with oil. You heat oil, and it causes the air to get sucked in. It's a way of getting a vacuum that's higher than a normal vacuum would give you. So it's an auxiliary vacuum. Anyways, that malfunctioned. The heating element stopped working. And we were getting a non-dynamic range because there was so much interference. It was exceeding our dynamic range for the instrument. So literally everything was just background. We couldn't see past the background because the background was just so bad. Okay? And that's just because the signal from the air. Well, air that was vacuumed to a fraction of the atmosphere, but still was too much. So when there is a linear response, the corrected analytical signal, the signal from the sample minus signal from your blank, will be proportional to the quantity of the analyte. The linear range of an analytical method is the range over which the response is going to be proportional to concentration. Literally, it's a linear range, right? You have a linear response. Okay? The dynamic range is the range over which it is a measurable response to the analyte, even though you may not be able to actually correlate those responses with a linear line, right? So even if the response is not linear, dynamic, you can still detect the difference. Okay? And yes, you could theoretically actually fit a curve to that. It's just much harder, and you get far greater error. Okay? So it's better to stay in linear range. You want any sort of accuracy. This is a calibration curve you're seeing. So an unknown protein sample gave an absorbance of 0.406. The blank had an absorbance of 0.104. How many micrograms of protein are in the unknown? So you would correct your absorbance using your blank, which the instrument typically does for you. That's why you take those blanks usually. That's literally what it does. It just subtracts it off. Okay? And that gives you 0.302. This would lie inside the linear range of your calibration curve, seen in 413. You rearrange the equation, 425 would give you this, the micrograms of protein in that sample, equal the absorbance minus this value over that value. Literally, that's just solving y equals mx plus b, right? There's your minus b, there's your slope. Everybody okay so far? Do the math, you get 18.2 micrograms, underscore 4, just so you have the extra digit in case you want it. Okay. By the way, your book's really nice because it gives you test yourself, in which it doesn't show you the work, but it gives you the answer. If you're ever unsure and you don't have a homework problem, which you usually do, you might want to test yourself, okay? All right, so blank solutions. Blank solutions can be prepared from the same reagents and solvents used to prepare standards and unknowns, but the blanks have no intentionally added analyte. There could be analyte in it, by the way. There sometimes is. Like, there's a very famous case of lead where the person was trying to determine the age of the planet. And he couldn't get rid of his lead in his blanks. So he finally had to like throw all of his equipment out of his lab, bleach the lab 4 times. It was, he finally got it though. The blank tells us the response of the procedure to impurities or to interfering species in the reagents. Most times you will have a response from the environment or the non-analyte components of your sample. Okay? You will have some sort of response. There is no method I can think of that will give you a 0. Okay? The blank value is subtracted from your measured values of standards prior to constructing the calibration curve. Can anybody tell me what this actually is? We have, remember how we had we started all this with types of uncertainties? And we said we have the randomized versus what? Systematic, right? This is actually systematic error, isn't it? And we're subtracting the systematic error out. Okay? This is an application of that. So the blank value is going to be subtracted from the response of an unknown prior to computing the quantity of the analyte, of the analyte in the unknown, because you have to subtract off all of the responses from everything else before you can measure anything about the analyte, right? Kind of like if you used a ruler, and you know how some rulers, the 0 part gets messed up? And so you got to do 1 to whatever you do. And you just subtract off 1 every time, right? Exact same concept. It's just in the real world, the 0 is always messed up, right? In fact, rulers are pretty much like that too, aren't they? Almost no rule I've ever used has a 0 that works. They're almost all damaged. That was a good example. That actually works nice.